Hello students, welcome to the student brand. This is your semester. Today topic is current electricity. Current electricity. Let's start discuss about current electricity, right? So electric current. So click on like button. Click on like button. So before starting the class, okay, so let me know those who are interested, those who are listening, those who are attending. So click on like button. I equal to, let me reach the target. I equal to Q by T. I equal to Q by T. So what is I? Current. So here we are talking about current. That is I. I is current. The rate of flow of net charge, the rate of flow of net charge through a cross-sectional area. Rate. So rate means with respect to time. Rate means with respect to time. Okay. The rate of flow of charge through a cross-sectional area is called electric current. Is called electric current. Actually it is average current. Average current. So the rate of flow of net charge. Here we are talking about net charge. So that's why it is a average current. And coming to the I equal to dq by dt. dq by dt is the instantaneous current. Instantaneous current. Instantaneous current. Understood or not? So what is that? I equal to q by t. I equal to q by t is the rate of flow of net charge through a cross sectional area is called electric current. I equal to q by t. I equal to q by t is the average current. I equal to dq by dt is the instantaneous current. I equal to dq by dt is the instantaneous current. Understood or not? Instantaneous current. So coming to SI unit of current. So we have to talk about. So we need to discuss about SI unit of current. What is the SI unit of current? SI unit of current is ampere. SI unit of current is ampere. 1 ampere is defined as 1 coulomb of charge flowing through unit cross sectional area per second. Okay. So 1 ampere is defined as 1 coulomb of charge flowing through unit cross sectional area per second. This is called 1 ampere. 1 ampere. Understood or not? And here you can see when the current is flowing in a conductor, this is the conductor. Okay. So current is flowing. Yes or no? So in the conductor, 1 electron is flowing. Will you say current is flowing? If 2 electrons flows, will you say current is flowing? 3 electrons, 4 electrons, 5 electrons? No. So there are number of charges, right? Positive charge, negative charge. There are number of charges are moving in the conductor. Then only we can say current is flowing. So here positive charge, negative charge, positive charge, negative charge, positive charge. That's why charge is quantized. Q equal to plus or minus Ne. Q equal to plus or minus Ne. Is it clear? Right. So on one electron, 1.6 into 10 power minus 19 coulomb. On one electron, 1.6 into 10 power minus 19 coulomb. In 1 coulomb, 1 by 1.6 into 10 power minus 19, then that is 1 by 1.6 into 10 power 19, then you'll get, so 1 by 1.6, 1 by 1.6, so 10 by 10 you can multiply, then you'll get 10 power 19, then you'll get 10 by 16, then you'll get 10 power 19. If you do this, you'll get 1 coulomb 6.25 into 10 power 18. 6.25 into 10 power 18 electrons. Is it clear or not? Is it clear or not? Check once. Check once. So I equal to Q by T, that is average current. I equal to dq by dt, that is instantaneous current. SI unit of current is ampere, SI unit of charge is coulomb, SI unit of time is second. So charge is quantized. Q equal to plus or minus Ne. Okay, so in the conductor, number of charges are moving, then only we can say current is flowing. On one electron, 1.6 into 10 power minus 19 coulomb. In 1 coulomb, 6.25 into 10 power 18 electrons are present. Understood or not? This is about electric current. This is about electric current. Understood or not? So now we will discuss about, we will discuss about the flow of charge can be obtained. Flow of charge can be obtained by multiplying constant current with the time interval. The flow of charge can be obtained. The flow of charge can be obtained by multiplying constant current. So first one, delta Q equal to I into delta T. Okay. The flow of charge can be obtained by multiplying constant current and time interval. Now, the flow of charge can be obtained. So if the current is a function of time, if the current is a function of time, if the current is a function of time, so the flow of charge can be obtained T initial, T final, I into dt. And coming to the third one, the flow of charge can be obtained by area under the IT graph. Area under the IT graph. Understood or not? So here you can observe. That is I on y-axis, T on x-axis. So the graph is here. Okay. So like this we can take. Like this we can consider. Understood or not? Once again see here. So I equal to Q by T. The rate of flow of net charge through a cross-sectional area is called electric current. That is I equal to Q by T. That is average current. Coming to instantaneous current. Current at particular instant I equal to dq by dt. That is instantaneous current. The flow of charge can be obtained by multiplying constant current with the time interval. And the flow of charge can be, if the current is a function of time, flow of charge can be obtained integral T initial T final I into dt, and the flow of charge can be obtained by area under IT graph. Understood or not? Just check once. Next one we will discuss about, okay, so based on magnitude and direction, current can be divided into two types. Based on magnitude and direction, so here one is DC, second one is AC. Okay, based on magnitude and direction. Based on magnitude and direction, current can be divided into two types. One is DC, another one is AC. Right? So the magnitude and direction of current, the magnitude and direction of current does not change with respect to time. Okay, with respect to time, magnitude and direction of current does not change. That current is called DC. That current is called DC. Example, cell. First one is cell, battery, and DC dynamo. DC dynamo. Okay. Coming to the alternative current. Both the magnitude and direction of current changes with respect to time. Both the magnitude and direction changes with respect to time. That is called AC. Alternative current. Example for alternative current, AC dynamo. AC dynamo. Right? So now, if the charge is moving in a circular path, so Q is a charge moving with the frequency F. If the charge is moving in a circular path with a frequency F, the current can be written as I equal to QF. I equal to QF. So the current will flow in the conductor due to motion of the electrons, movement of the electrons, right? Yes. Understood or not? So this is about DC and AC. So next one, drift velocity and relaxation time. Drift velocity and relaxation time. So we'll discuss about drift velocity and relaxation time. Let's discuss about it. Drift velocity and relaxation time. Right? Yes. Drift velocity. Drift velocity and relaxation time. Okay, so when electron is moving in a conductor, okay, when electron is moving in the conductor, it experiences some force, right? So when electrons are moving in the conductor, so those electrons experience force, right? So here I am taking this conductor, current is moving like this, this is I. So here positive, no electrons, right? Drift velocity, this is the drift velocity, reading. And now we know, so it experience some force. When electrons are moving in a conductor, experience force. Okay. So F equal to E or QE, right? So when electrons are experiencing force, then it will produce acceleration. Who will produce force? When force is acting on the some substance or electron, then automatically the electron comes under motion. Yes or no? Electrons start moving from that position. Then the force which is experiencing by the electron, okay, so electron will experience the force, then automatically force will produce acceleration, right? Yes. So that's why F equal to ma, then ma equal to E QE equal to A equal to E by M and QE by M. Understood or not? So coming to the drift velocity. So drift velocity and relaxation time. Drift velocity. First one is drift velocity. Drift velocity, that is VD. So we'll discuss about drift velocity briefly. So here you can observe this is the conductor. Electron is moving. Okay, electrons are moving in the conductor. Electrons are moving in the conductor. Right? When electrons are moving in the conductor, normally suppose if you take, there is a running race. So they'll be having their track. Okay, so the path in which they have to go. Yes or no? So in the ground you can see ground. So people are there, so they can run. So there is so much space is there, they can go. Here in the conductor, so electron has to move in a closed path, in a less path, within the less area. Okay. So there are more number of electrons, not only one. Okay, so the many members are moving in one direction, then what happens? One person will let another person, that person will let another person, that person will let another person, like that keep on, collisions will take place. Here also the same thing. So I'm moving with some velocity. So I'm moving in a particular direction, so I'm moving with some velocity. So I'm moving. But besides of me, few people are moving. Then what happens? So me either I'll go and hit or they will come and hit me. Not like this, like this. Okay. So when if we are going to hit others, then what happens? Collisions will take place. So before I'm going some velocity, right? After colliding with another, then my speed will decreases, their speed will increases, right? So they will move with a different velocity, maybe more than initial, more than previous velocity, right? So here also the same thing, when electrons are moving in a closed conductor, when electrons are moving in a closed path, one electron will hit another electron. So here you can see, one electron will hit another electron, this electron will hit another electron, this electron will hit another electron. Then keep on collisions will take place. So this will be having some velocity. This will be having some velocity. Okay, then different electrons having different velocity. After collisions, their velocity also changes. Okay, the average constant velocity of electrons are moving in a conductor. This is average velocity. Understood or not? Average velocity. Drift velocity is nothing but average velocity of an electron moving in a conductor. That is called, say, average constant velocity. We can see average constant velocity of an electron moving in a conductor. So electrons, we can see electrons are moving in a conductor. Understood or not? So that is called drift velocity. Now we will discuss about relaxation time. Second one is relaxation time. Okay. Relaxation time. So what is relaxation time? So just now I mentioned one point, that is, when electrons are moving in a conductor, right? So one electron will hit another electron because they are moving in a closed conductor. They are moving in one direction, then automatically collisions will take place. So collisions will take place between electrons. That collisions, okay, so suppose this electron will hit this electron. Okay, so after that again, so suppose if you take this electron will tear the electron, this electron is going to hit this electron, this electron will going to hit electron. Okay, so one electron is going to hit another electron, that electron is going to hit another electron. Understood or not? Collisions will take place. So whatever it may be, so definitely collisions will take place, right? But so between one collision to another collision, there must be time gap, right? So time gap will be there. Yes or no? So that time gap, the average time between two successive collisions. So between one collision to another, one after another. Okay, between two successive collisions is known as relaxation time. Relaxation time. Understood or not? The average time between two successive collisions. Okay, so that is called relaxation time. Understood or not? So Vd is the drift to velocity. So tau is the relaxation time. So that is about drift to velocity and relaxation time. Understood or not? Now we will discuss about current and drift to velocity. 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 Okay, shall we discuss about current and drift to velocity? Current and drift to velocity. So here you can see in the conductor electrons are moving. In the conductors electrons are moving. So here you can see this area of the cross section. This is the area of the cross section. So this is area of the cross section and this one is the length. Okay, and in the conductor within this volume electrons are moving. So this is the drift velocity. Drift velocity. Understood or not? So normally what is the velocity formula? V equal to L by T. So sorry, L by T. V equal to L by T. Yes or no? V equal to L by T. L equal to V into T. That is Vd into delta T. Vd into delta T. Understood or not? So now this is the Vd into delta T. So now you can see here. So volume of the conductor, volume equal to volume. Volume means what is the formula? Length into area of the cross section. Volume is nothing but length into area of the cross section. What is the length? Vd into delta T into A. Next one, number of electrons are present. Number of electrons are present in the particular volume. Number of electrons present in the particular volume. Small n is the electron density. Small n is the electron density. Now you can see n Vd delta T into A. Okay. So now we know charge, the flow of charge. What is the flow of charge formula? So delta Q equal to N into Vd into delta T into A into E. Yes or no? Into E. Understood? Now, so what is the current formula? I equal to delta Q by delta T. That is nothing but, so N E A V D delta T by delta T. So here delta T get cancelled. Yes or no? Shall we cancel delta T? Shall we cancel or not? After cancelling, what will be the remaining? I equal to N E A V D. Okay, now current density formula. What is the current density formula? Current density J equal to I by A. Current density. Current density. Current density J equal to I by A. So what is I? N E A V D by A. So A get cancelled. Shall I cancel A? Okay. So I am cancelling A. So what will be the remaining? I equal to N E V D. Understood or not? One check it here. One check. Current and drift velocity. Current and drift velocity. Understood or not? Just check once. So, normally area of the cross section. So, I am taking this area of the cross section. This is area of the cross section. Electrons are moving in the conductor. So, this is the drift velocity. So, normally velocity equal to displacement by time taken or length by time taken. So, if you are taking magnitude. So, L equal to Vd into dt. L equal to Vd into delta t. So, Vd into delta t. Volume. What is the volume formula? Length into area of the cross section. What is the length? Vd into delta t and area of the cross section A. So number of electrons present in the particular volume. Number of electrons present in the particular volume N. So N is the electron density N Vd delta t into A. So this is the volume and so N. Now delta Q. Delta Q equal to, so N Vd delta t into A into E. Okay, quantization of charge. So Q equal to plus or minus any, right? So any we are taking here, delta Q equal to N Vd delta T into A into E. I equal to delta Q by delta T. N E A Vd delta T. So delta T get cancelled. Delta T get cancelled. I equal to N E A Vd. N E A Vd. So coming to the current density. What is the current density formula? Current density equal to J equal to I by A. So what is I value? N E A V D. That is N E A V D by A. A get cancelled. What is the current? So sorry here. Current density, right? Current density J. Current density J value. So J here. Current density J equal to N E V D. Understood or not? Is it clear? If it is clear, just give a like button. Okay, now click on like button if it is clear. If you understand. So if explanation is good, just let me know. So this is the current and drift velocity. Current and drift velocity. So next one, we'll discuss about resistance and resistivity. 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 So now, what is a resistance? So normally if you want to go on vacation, like like a field trip or like that, so you're going on trip or you're going to like vacation space like this, so like out, like you can say some like here, so your parents will stop you. Okay, so it is not the right time. Now exams are going on, now preparation time, now so like you have to prepare still concepts. Okay, some festival is there in our home, some like important work is there. Okay, so in our home, so now it is not correct time to go like field trip or like that they will tell, like sometimes in some cases. Okay, not every time, not all cases, so it depends on different situations, right? Yes. So here you want to go, right? But your parents are opposing. Your parents are opposing. Here also, electrons current want to go through the conductor, but it opposes. So the one which is opposing the electric current to flow, that is called a resistor here. Here some appreciable resistance. It completely does not stop. It opposes some extent. So suppose materials. There are conductors, insulators, semiconductors, and coming to resistors. Sir, conductors, it allows the current to pass through it. Point number one. Insulator, it does not allow current to pass through it. Second one. Coming to third one. So the opposition will be intermediate. Allowance also. So allowing also it will be intermediate between conductor and insulator. Whereas resistor, so it opposes but appreciable resistance. Okay, some appreciable resistance is there, that is called resistor. Okay, so in our house, electrical bulb, fan, TV, fridge, all these things are resistors only. So some it will oppose, it does not oppose everything. Okay, some appreciable resistance is there, that is called a resistor. That is called resistor. So the device which is used to oppose the electric current, the device which is used to oppose the electric current is called resistor. The phenomena of opposing the electric current, the process which is opposing the electric current, that is called a resistance. The device or a device which is used to oppose the electric current in the circuit, in an electric circuit, is called a resistor. Understood or not? So resistance is depends on length of the conductor. Suppose one activity I will show you. So normally there is one activity related to resistance. So I am taking this nichrome wire. L length. Nichrome wire I am taking this L length. So this is the A, B, L length and area of the cross section is A. So don't get confused. So between A and cap. Okay. So I am removing this one. Instead of that, just simply we can say conductor. So next one, twice of the length. So you have to connect this wire to the circuit. Okay, to an electric circuit. Then identify the current direction. So like current in the ammeter. Okay, you have to observe the current in the ammeter. Next one, you can see same length is doubled, area of the cross section is same. So here area of the cross section A, length is L. Here, so increase the length. So twice of the length and area of the cross section is same. Area of the cross section is same. Again you have to connect. So case 1, case 2. So in the second case you have to connect this wire to an electric circuit or to observe the reading in the meter. Okay. So then third case, area of the cross section is twice. So this wire is resistor. So why out nichrome wire I am taking? Nichrome wire. So I am taking the nichrome wire. So in 3 cases nichrome wire only. Nichrome wire. In the 3 cases, case 1, case 2 and case 3 also, nichrome wire only I am taking. Nichrome wire only I am taking. Here, area of the cross section is twice, length is same. Length is same as first case. As like first case, so what length we took? So the same length will be considered in the third case also. Okay, same length, but area of the cross section is doubled compared to the first one. Now, I am taking the fourth case. So area of the cross section is A. But this case, so area of the cross section is A, length is L, but this case I am taking copper wire. So in the 3 cases I am considering the nichrome wire. In the fourth case I am considering the copper wire. Then connect this wire in an electric circuit and observe the ammeter reading. Understood or not? So once again, so nichrome wire, case 1, length of the wire is L and area of the cross section is A. And in the second case, length of the wire is doubled. Area of the cross section is A. And in the third case, area of the cross section is twice. Length is same as previous in the first case. And coming to the fourth case, so same length, same area of the cross section as like first case. But here, instead of nichrome wire, in these 3 cases I am taking nichrome wire. But in the fourth case I am taking the copper wire. So different material. So here you can observe different cases, case 1, case 2, case 3. In these 3 cases, observe the ammeter reading. And in fourth case also observe the ammeter reading. So by observing all these 4 cases, we can conclude that by observing all these 4 cases, okay, so reading of ammeter in the 4 cases. So that is represent here, that is R is directly proportional to L, means resistance is directly proportional to length of the conductor. Okay, if small length, less resistance. If you increase the more, twice, then resistance also increases. If you increase still length, resistance increases. So it's directly proportional. If length increases, resistance also increases. Understood or not? And the second case, so next case is area of the cross section. So now like you can observe the water pipe you can observe. If more area is there, so more water will come out. Less area is there, less water will come out. Understood or not? You can observe the tap. Okay, so once if you can open very less water, you can open little more compared to previous. Still you can open, then little more. Then if completely open, compared to the previous cases, the water will come out more. So area of the cross section is increasing each and every time. Yes or no? So area of the cross section is increasing, then resistance is decreasing. Understood or not? So that's why resistance is inversely proportional. Resistance is inversely proportional to area of the cross section. So R is directly proportional to L by A. R equal to rho into L by A. Understood or not? So now you can observe here. Now we can observe resistance. SI unit of resistance is ohm. Ohm. And coming to the resistance depends on temperature. Resistance depends on nature of the material. In the last case, Nature of the material. In the last case, instead of nichrome wire, so I took copper wire. Yes or no? So in the last case, instead of nichrome wire, I said connect copper wire. Then observe the reading of ammeter. Understood or not? Last case in fourth case. So among four cases, in the last case, I mentioned instead of nichrome wire, I mentioned copper wire. You can take, sir, why only copper wire? We can take remaining wires. Yes, you can take. Okay, just by you have to change the material. Okay, my idea to express is you have to change the material. Okay, so if you change the material, automatically resistance also changes. Resistance also changes. Understood or not? So that is what I am trying to say. That is what I am trying to say. Understood or not? Now resistivity rho equal to RA by L. Resistivity rho equal to RA by L. So rho equal to SI unit. So this is very important. SI unit of resistivity is very important. SI unit of resistivity is very important. Understood or not? Understood or not? So here you can observe. Here you can observe ohm meter square by meter. Meter get cancelled. So ohm meter. Understood or not? Ohm meter. So ohm meter. So that is nothing but ohm meter. And resistivity depends on temperature. Sir, you didn't explain about temperature. Yes, next point is about temperature only. Completely about temperature. So based on temperature, relation between resistance, resistivity and temperature, based on that one questions will come. So we'll discuss that point briefly. So now here resistivity also depends on temperature. Resistivity depends on nature of the material. Nature of the material. Okay. Nature of the material. Understood or not? Okay. So observe these points. Observe these points. So check once. Check once. Is it clear or not? Is it clear or not? Okay, next one. I will explain about temperature dependence of resistance. Temperature dependence of resistance. So if you like the content, if you like the explanation, click on like button. So let me know. So if it is clear or not, you understood or not, just click on like button, then I will get to know. You understood the concept is clear, then I can move forward to explain the next concept with a greater velocity, greater speed, greater amplitude, greater momentum. Next one, temperature dependence of resistance and resistivity also, both will discuss. Temperature dependence of resistance. So now you can see temperature. So I'll give one incident. So I will explain one situation. So here in an incident, in that two things will happen at a time. Okay, at a time, two things will happen. The first one is the very first one is the very first one, and after the second one. The very first one is as soon as you increase the temperature of the conductor, or the temperature of the conductor increases, or the material of the conductor increases, then what happens? The free electrons in the conductor increases. The free electrons in the conductor increases, and at the same time these electrons are moving with greater amplitude, and ions of the conductor moves with greater amplitude. Understood or not? As soon as you increase the temperature of the conductor, free electrons in the conductor increases and ions of the conductor moves with greater amplitude. The very first situation. If the electrons are moving with greater amplitude, then automatically conductivity increases or not? Conductivity increases. If conductivity increases, resistance and resistivity decreases. Conductivity increases, resistance and resistivity decreases. This is the very first situation. And coming to the next situation is if electrons are moving with greater amplitude in a conductor, they are moving very fast with a higher amplitude, greater amplitude. They are moving with greater amplitude. Then what happens? Then collisions will take place. So within a closed enclosure, within a conductor, electrons are moving with greater amplitude, then automatically collisions will take place between electron to electron, between electron and electron, right? Yes or no? Then if the electrons, if the collisions are happening, if the collisions are taking place between the electrons, then what happens? Resistance and resistivity increases. Resistance and resistivity increases, conductivity decreases. Resistance and resistivity increases, conductivity decreases. Understood or not? So by this we can conclude that if temperature increases, resistance and resistivity of the material also increases. Right? Yes. So now you can observe R is directly proportional to L. R is inversely proportional to area of the cross section. R is directly proportional to L. R equal to rho into L by A. I will tell one more point. That is, if temperature of the material or temperature of the conductor increases, then length and area of the cross section of the particular material also changes. Yes, and length and area of the cross section of the particular material, then the one which is increasing the temperature. Yes, and the one which is increasing temperature or the temperature of the material is changing to that particular material, length and area of the cross section also changes. But actually those changes, length and area of the material changes, those changes are very quite small. Those are quite small. That's why so we are taking R is directly proportional to rho. So L by A is constant. L by A is constant. Understood or not? L by A is constant. So now we can take. So alpha is the temperature coefficient of resistance. Alpha is the temperature coefficient of resistance. So that's why we can write RT equal to R naught 1 plus alpha into T minus T naught. Then RT equal to R naught plus R naught into alpha T minus T naught. Then RT R naught equal to R naught alpha T minus T naught. Then alpha equal to RT R naught by R naught into T minus T naught. So alpha is the temperature coefficient of resistance. If it is so, we can also write, because so R is directly proportional to rho. Then alpha equal to rho naught by rho naught into T minus T naught. Sir, what is this rho and rho naught? So rho naught is the initial resistivity and rho T is the resistivity at particular temperature. resistor at temperature T. So that's enough. Understood or not? Just check once. Just check once. If it is clear, if the concept is clear, if the explanation is clear, if the explanation is good, just click on like button. Okay. So let me know the concept is clear to you all. Okay. Next one, Ohm's law. Ohm's law. Ohm's law. Okay, so check once. We'll discuss about Ohm's law. Just 2 minutes. 2 minutes. Okay, so next we'll start discuss about Ohm's law. Let's start. Ohm's law is nothing but the potential difference across the ends of the given metallic conductor. Ohm's law. Ohm's law is nothing but the potential difference across the ends of the given metallic conductor is directly proportional to current flowing through it at a constant temperature. So I'm taking this the material. So like a resistor, this is the potential difference. Current is flowing here. So V is directly proportional to I. V equal to IR at a constant temperature. At a constant temperature. The potential difference across the ends of the given metallic conductor, so your resistor, so across the metallic conductor is directly proportional to current flowing through it. So V is directly proportional to I and V equal to IR at a constant temperature, and physical conditions also same. Physical conditions also same. Understood or not? So that is very very important. That is very very important. Now you can see for Ohm's law, for ohmic conductor, first one is the graph is straight line for ohmic conductors. Ohmic conductor, the graph is straight line for ohmic conductors. So V on y axis, I on x axis. The graph, that is slope. Slope equal to tan theta equal to r. That is a theta. Here is the theta. Tan theta equal to r. Tan theta equal to r. So this is for ohmic conductors. So coming to non-ohmic conductors. Non-ohmic conductors. So the graph is curved for non-ohmic conductors. So here V on y axis, I on x axis. V on y axis, I on x axis. So here V1, this one is the I1, V2, and here is the so this I1, I2, I1, I2. Okay, so you can see P, P, Q. So V1 by I1 equal to R1, that is at P. V2 by I2 equal to R2, that is at Q. But R1 is not equal to R2 for non-ohmic conductors, non-ohmic resistors. Understood or not? So just check once. So here you can see non-ohmic conductors V1 by I1 equal to R1, V2 by I2 equal to R2. So R1 is not equal to R2, right? Next we will discuss about, now we will discuss about electromotive force. Electromotive force. Electromotive force. So when you connect the cell to the circuit, so I am taking here. So we know that automatically the current will pass from, so positive charges will move from positive terminal to negative terminal. That is nothing but high potential to low potential. So high potential to low potential. But so the positive charge is there at low potential. So in the cell. Okay. So the positive charge at the low potential and high potential. The influence or the work done to bring unit positive charge from low potential to high potential or from negative terminal to positive terminal of the cell is called electromotive force. Work done by the cell, work done by the battery on the positive charge. Okay, so E equal to W by Q. This is called electromotive force. Electromotive force. Understood or not? So I hope it is very clear. So that is about electromotive force. Next one, resistors are connected in series combination. Resistors are connected in parallel combination. Let's start discuss about resistors are connected in series combination. Resistors are connected in parallel combination. Resistors are connected. Resistors are connected in series combination. Series combination. Resistors are connected in series combination. Okay. So now you can see I am taking 1, 2, 3. R1, R2, R3. So I am connecting the volt ammeter. So here is the battery. So current is flowing. Across R1 I am connecting V1. Across R2 I am connecting V2. Across R3 I am connecting V3. So positive, negative, positive, negative, positive, negative. So current is flowing here. And here you can observe throughout the circuit. If you observe this circuit, so R1, R2, R3, so across R1, V1, across R2 V2, across R3 V3. Okay, so we connected. So this is the battery, ammeter, switch. Now throughout the circuit current is same. Throughout the circuit current is same. So that is nothing but IS equal to I1 equal to I2 equal to I3 equal to I. IS equal to I1 equal to I2 equal to I3 equal to I. Understood or not? From Ohm's law, V equal to IR. From Ohm's law, V equal to IR. So now V is equal to V1 plus V2 plus V3. That is nothing but IR is equal to IR1 plus IR2 plus IR3. So now I am taking I common. That is I you are taking common R1 plus R2 plus R3. Shall I cancel II? Shall I cancel II? Okay, so now RS equal to R1 plus R2 plus R3. So here, if n number of resistors are connected in series combination, if n number of resistors are connected in series combination, RS equal to NR. Once again observe here. So R1, R2, R3, across R1, V1, across R2, V2, across R3, V3. So throughout the circuit current is same. IS equal to I1, I2, I3, I. Okay, so Vs equal to here. Potential difference is different. Right? Potential difference is different. That's why Vs equal to V1. Sir, what is Vs? So overall potential difference in series combination. So Vs equal to V or V effective V equivalent also we can write. V effective or V equivalent or Vs also we can write. Vs equal to V1 plus V2 plus V3. So we know from Ohm's law V equal to IR. From Ohm's law V equal to IR. So IR is equal to IR1 plus IR2 plus IR3. I am taking common, I get cancel. RS equal to R1 plus R2 plus R3. That is if n number of resistors are connected in series combination, RS equal to NR. RS equal to NR. Now we'll discuss about n number of resistors are resistors are connected in parallel combination. After that, n number of resistors are connected in parallel combination. Okay. So now resistors are connected in parallel combination. Resistors are connected in parallel combination. Let's start here. Right? So parallel combination. That is, so here you can observe 1, 2, 3. Ohm's law. Voltmeter, ammeter. So voltmeter cannot connect. So in series only ammeter. Here we have to connect voltmeter. So here R1, R2, R3. R1, R2, R3, I1, I2, I3. So this is the current. So positive terminal, negative terminal, positive terminal, negative terminal, positive, negative current is flowing. So throughout the, so here you can observe potential difference is same. That's why Vp equal to V1 equal to V2 equal to V3 equal to V. V equivalent we can take. V effect also we can take. Now V equal to IR. I equal to V by R. V equal to IR. I equal to V by R. But current is same, right? So current is different, right? Potential difference is same. Current, see, through R1, I1. Through R2, I2. Through R3, I3. So current is different. Current is different. That's why IP equal to I1 plus I2 plus I3. That is nothing but V by RP equal to V by R1 plus V by R2 plus V by R3. So I am taking V common. 1 by Rp equal to, so V I am taking common 1 by R1, 1 by R1 plus 1 by R2 plus 1 by R3. So V will get cancelled. So 1 by Rp equal to 1 by R1 plus 1 by R2 plus 1 by R3. So 1 by Rp equal to 1 by R1 plus 1 by R2 plus 1 by R3. So if n number of resistors are connected in parallel combination, 1 by Rp equal to n by R. So Rp equal to R by n. Rp equal to R by n. Understood or not? So once again check here. So R1, R2, R3 are connected in parallel combination. R1, R2, R3 are connected in parallel combination through R1, R2, R3. So through for three resistors, potential difference is same. So we are connected to one junction this wire and another junction another end. So Vp equal to V1, V2, V3 equal to V. So but current is different, right? Through R1, I1, R2, I2, R3, I3. So from Ohm's law, V equal to IR, I equal to V by R. Now IP equal to, so current in parallel combination, IP equal to I1 plus I2 plus I3. So we can take the formula. If n number of resistors are connected in parallel combination, so 1 by Rp equal to n by R, Rp equal to R by n. Understood or not? So I hope it is very clear. Next one, Kirchhoff laws. Actually, most of the circuits we may not, so all circuit cannot reduce to series and parallel circuit, right? Some circuits we may not reduce. So that time we will use Kirchhoff laws. We'll use Kirchhoff laws. Okay, so let's discuss about Kirchhoff laws. So here one is junction law, another one is loop law. Loop law. One is junction law, another one loop law will use. So we'll see. One is junction law, another one is loop law. So Kirchhoff laws. So first one is junction law. Junction law. Sum of the current reaching to the junction is equal to sum of the current leaving from the junction, or the algebraic sum of all the currents meeting at a point equal to 0. I1, I2, I3, I4. So here you can observe the algebraic sum of all the currents meeting at a junction equal to 0, or sum of the currents reaching to the junction is equal to sum of the currents reaching from the junction. Here you can see I1 plus I2 are reaching to the junction, coming to I3 and I4 leaving from the junction. So that is the junction law. Coming to the loop law, okay. Loop law. Oh my God. Loop law. So here 4 points. Point number one. Point number one. So you are moving from A, B, negative terminal, positive terminal. You are moving. This is the path. So you are moving from negative terminal to positive terminal of this cell. Negative terminal to positive terminal of the cell. Then EMF is positive. EMF is positive. Coming to the second one. So the path is very important. With which path you followed, which path you consider, that is very important. So this is a path. This is a path, positive, negative. So the EMF is negative. So you are moving along this path, negative terminal to positive terminal. So EMF is positive. And you are moving from positive terminal to negative terminal. EMF is negative. Okay, that is very, very important. And coming to the third one, so you are moving through resistor. So along the current direction, this is the current A and B. So I am taking this the path. The path is very important. Along the path, you have to consider the path. Now, yeah, that is true. Conversion of charge. So here you can observe minus IR term. And coming to the fourth one, so you are moving opposite to the current direction. This is A and this is B. So you are taking the path along this direction. Then IR term is positive. IR term is positive. Understood or not? These 4 points are very, very important. So follow carefully. Follow carefully. So Kirchhoff laws and loop law. Kirchhoff laws under that junction law and loop law. Junction law and loop law. Is it clear? So next one, so we'll discuss about internal resistance and heating effect of electric current. Internal resistance and heating effect of electric current. Internal resistance and potential difference. Same loop law we will use for internal resistance. So internal resistance. Internal resistance. When electrons are moving through electrolyte, when electron is moving through electrolyte, it experience, or moving through the cell, it experience some resistance. If opposition is there for electron, automatically voltage drop is there, current will decreases. So negative IR, right? So that's why I'm taking here this cell, this is the cell, internal resistance R, this is the EMF, positive to negative, A, B, you are moving the along the current direction, this is the path, then E, potential difference equal to E equal to IR. So like this we can apply the junction law. Loop law. We can follow the loop law. This is the loop law. So along the path, so current and current is there. That's why minus IR term. So negative to positive you are going. So EMF is positive. So potential difference V equal to E minus IR. That is internal resistance. Coming to heating effect of electric current. 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 Okay. So we know potential difference. What is the formula potential difference? V equal to W by Q. So potential difference is nothing but V equal to W by Q. So W equal to V into Q. So P equal to W by T. That is VQ by T. That is V into Q by T is current. Q by T is current, right? Q by T is the current. Yes or no? Then P equal to VI. Energy is given. Energy is given to the conductor. That is E equal to P into T. That is VI into T. So now heat produced in the conductor, that is IR into I into T. That is I square RT. I into T. So H equal to I square RT. Is it clear? Heat produced in the conductor is directly proportional to time. So heat produced in the conductor is directly proportional to resistance. Heat produced in the conductor is directly proportional to square of current. Okay, so this is about heating effect of electric current. Understood or not? So next one, grouping of cells. Grouping of cells. Grouping of cells. Grouping of cells. Cells are connected in series combination. Cells are connected in series combination. Okay, cells are E and R of each cell is same. Okay, so then net EMF. Net EMF equal to NE. Net EMF equal to NE. And net internal resistance. Net internal resistance, that is NR. Total resistance. Total resistance is total resistance. Total resistance. Total resistance equal to this capital R you have to add. So R plus NR. Then current equal to net EMF by net or total resistance. We can say total resistance. Total resistance. Total resistance. Okay, that is I equal to net EMF is nothing but NE, and net so total resistance is nothing but R plus NR. Okay, so that's enough. That is about cells are connected in series combination. Cells are connected in series combination. Okay, so this is series combination. Series. Next, the cells are connected in parallel combination. Now we'll discuss about cells are connected in parallel combination. Cells are connected in parallel combination. Let's start a parallel combination. Oh, resistors. Cells you have to draw. Now cells are connected in parallel combination. Net EMF, net net internal resistance, net internal resistance equal to R by N. Total resistance R plus R by N. Okay, so I equal to net EMF by total resistance. Now net EMF is E, net resistance is R plus R by N. That is current. Understood or not? Just check once. Just check once. Is it clear? So thank you so much for joining, attending, listening, interacting. Okay. So thank you so much for interacting with me. So do like, share and subscribe to Student the Brand. If you like the content, if you like the explanation, share to everyone, inform to your friends, ask your friends to join to the class, check the class. So if it is clear, if it is good, then ask them to subscribe the channel. Thank you so much. We'll see you in the next class. We'll see. Thank you.